Okay, I think we're on. Okay. Welcome to the prize lecture for the Wilkinson Prize for Numerical Software. I'm Jorge More. I'm the chair of the selection committee. Before we get started, a little bit of history may be helpful. The prize was started by three organizations: Argonne National Laboratory, the National Physical Laboratory, and the Numerical Algorithms Group, about a little bit more than 30 years ago. From 1991 to 1995, we gave out this prize at SIAM. But in 2015, we approached SIAM to take over the sponsorship of the prize. SIAM agreed. There was a little issue with the endowment of the prize, but this was resolved by generous gifts from the three original sponsoring organizations. Today is the first time that the Wilkinson Prize is being given under SIAM sponsorship. The selection of the winner is never an easy thing, but we had an excellent selection committee that made this process relatively easy. Those here, Mike Haru, Randy Levesque, and Kathy Yellick. It was a pleasure working with them. On previous occasions at SIAM meetings, the chair of the selection committee would say some nice words about why the particular winner was selected. But under SIAM sponsorship, they get to deliver a lecture, so they will tell us all the good things about the selection. So before I cede the floor, let me, it is actually my duty to read the citation for the prize. The 2019 Wilkinson Prize for Numerical Software is awarded to Jeff Besenson, Stefan Karpinski, and Viral Shaw for the development of Julia, an innovative environment for the creation of high-performance tools that enable the analysis and solution of computational science problems. Julia allows researchers to write high-level code in an intuitive syntax and produce code with the speed of production programming languages. Julia has been widely adopted by the scientific computing community for application areas that include astronomy, economics, deep learning, energy optimization, and medicine. In particular, the Federal Aviation Administration has chosen Julia as the language for the next generation airborne collision systems. And now, Viral Shaw will start.
Right. Thank you for that wonderful introduction, and we are all honored to be here today. I think one of the things that we learned as we were applying for this prize is that it's an early career award, and so our fourth collaborator, Alan Edelman, is not a recipient of the prize, but he's here with us and to support us. So that's Alan right there, I think. It's been a wonderful journey for us. SIAM has been, SIAM conferences have been something that I have personally been to as a grad student for the longest time, and as have many of us. And many of the ideas in Julia that we are going to talk about today were formed, looking up to many of the people who we've interacted with over the years out here. So without further ado, jumping right into solving the two-language problem. The two-language problem is a phrase we coined to basically capture this notion of the necessity that people believe that you have to always write programs in two languages. Prototype in Python, rewrite it in C. Prototype it in MATLAB, rewrite it in C++. Pick the two languages that you want, but there was always this belief, and fairly widely held, that productivity and performance could not go together. And that was the premise with which we started the Julia project. We actually fondly remember how exactly the project got started. It was in 2009. And Stefan and I were actually tossing a Frisbee at the Ultimate Field in Santa Barbara. At the same time, Jeff and Alan were discussing the same ideas in a parking lot right here in, oh, not here, but in Boston. And one thing led to another, but the most amazing thing that I recollect out of this experience was that 3 days later, it was clear we are going to start a new language. 3 days after that, there was an initial parser. In a couple of weeks, we were writing the first array libraries and random number generators and all the stuff that you see in Julia today. We put this slide together based on all the machine learning frameworks that we see, which I think greatly show what the problem is, what the two-language problem is. So you see all the famous TensorFlow by Google, PyTorch by Facebook, Caffe also Facebook, there's CNTK from Microsoft. And you can see that all of these have this huge component of C++ and Python and CUDA and all these different systems together. And it's really hard to program. The teams are incredibly large, and it's a complex project. But Flux is a pure Julia deep learning framework, which runs on GPUs, which runs on TPUs, and it's 100% Julia. And I think this is an amazing outcome from the Julia community and the Julia project overall. So I think that we have reached a time now that it is possible to imagine productivity and performance can go hand in hand together. Now, as we delve into the complexities of what the Julia language needs to be able to do, one of the slides, one of the things that we found very interesting early on and that drove us was this expression of polymorphism in linear algebra. And it basically goes on to say that for all the linear algebra problems, all the different matrix types, all the different data types, all the machine architectures, all the communication topologies, and programming interfaces provide the best algorithms available. And specifically in this working note, Demel and Dongara say that they specifically do not talk about programming languages, and that's not part of this discussion. And they chose to do it in Fortran when they did this, when they did LAPAC and ScalaPack. We believe that Julia is now at a stage where maybe it could be a choice for some of these tools as they're built. And we are going to sort of double click on some of these statements, some of this polymorphism nested for loop in the next few slides. So the first one I wanted to touch upon was a little bit about the Celeste project and parallelism. And this is an amazing scientific project that was run in collaboration with a number of institutes. It ran at petascale on the Cori machine at Lawrence Berkeley. And it was basically trying to catalog all the visible objects in the universe from the Sloan Digital Sky Survey. To our knowledge, this was the very first dynamic high-level language achieving petascale running on 650,000 cores. We are currently trying to scale this up by another factor of 1,000 and get to an exaop on Summit with a physics-based GAN. And so, stay tuned. And maybe we'll have something to report soon. Now, this particular problem was very interesting, and it highlights some of what Julia is able to let us do, which is it had this strange matrix structure. All the bits that are black are actually places where computation doesn't need to happen. And then the things that are in the same color are where computation needs to happen at the same time. And so you take this abstract matrix structure, and you want to represent it in a different way where all the same colored blocks are together. And this was done completely in Julia for this thing, and this is what we were able to express reasonably well using all our type system and machinery that Jeff will talk about soon. So I won't delve into it too much. But this addresses one of those things in the Demel and Dongara nested for loop there. Another topic that comes up when you're trying to do scientific computing at scale is, can this thing run on GPUs? I think many of you in the audience probably have tried out Julia and have run it on a variety of different architectures. And GPUs are incredibly interesting and the only way to get performance today. So we have a backend, CUDA-native.jl, which is completely, which generates completely native CUDA assembly kernels, and you can see the code on the left-hand side and the generated assembly on the right-hand side. And this provides the full CUDA programming model. Of course, the larger question that we keep asking ourselves is, can we abstract the programming model to be even more accelerator independent and provide a more Julian API on top of these things? Now, you'd wonder, is this Julia code gen for GPUs any good, right? Like, don't you have to just absolutely use CUDA and C++ to get the best performance? This is the Rodinia benchmark suite that's widely used by a lot of GPU researchers, and it turns out that the quality of our code generation is pretty good, and on most of the kernels, we actually end up doing a little bit better than CUDA itself. And now, to many people, it might sound like this is, like this may be like a violation of the speed of light, like how can you go faster than CUDA and C? And it turns out that the story is, in short, the story is simple, that NVIDIA did not open source its LLVM backend, and the one that was in LLVM was heavily improved upon by Google. And because we use LLVM, we're able to get all these benefits of running on different architectures with all the contributions from the community. And so we are quite amazed and proud of this achievement, which was actually done by Tim Bessard out here. I don't know if I can point. Yeah. Tim Bessard at Ghent University. A lot of my slides in the first third of the presentation are about what everyone else has built on Julia, and then we're going to dive down into what's inside. Another exciting architecture, the fastest matrix multiply units around nowadays are the TPUs, and largely used for deep learning, but we are trying to figure out what else can we do except deep learning on these things. Of course, we are now in pure Julia able to achieve the same performance on ResNet using a full TPU pod as Google itself. And this is, I think, an exciting time for HPC, where new kinds of hardware have come back into the limelight, and we're trying out new ideas. Now, one of the things that powers many of these computations is, of course, automatic differentiation. And without delving too much, this is a reverse mode autodiff example, and it works on the SSA form intermediate representation inside the Julia compiler. It's a tool called Zygote. The key thing I wanted to bring out here is that we've been able to design a system that is flexible enough that researchers can actually go in and add new compiler transforms and passes and build things into Julia that were not originally envisioned. So for example, all our GPU code generation capabilities do not live inside the base Julia compiler. They're an add-on package. The TPU compiler is an add-on package, and you don't have to recompile Julia for any of this stuff. Zygote is an add-on package, and all of these things come together and compose reasonably well. And this is why we believe that the Julia community has come this far in what we believe is a reasonably short time frame for a programming language, which often takes a decade or two to achieve a critical mass. An example of this composability is the differential equations ecosystem. So if you look at the code on the left-hand side, unless you look at it closely enough, you might wonder what's the big deal. This is just a regular ODE defining the pendulum, and you're solving it. But if you look a little close enough, you see that there are these plus-minus signs out here. So instead of just the values, we are actually providing values with uncertainty estimates. And the differential equation solvers written by Chris Rackauckas, they were written for working on double precision numbers. Maybe once in a while you throw in a single or a half precision. But what if you wanted to throw in a data type that was never imagined when the solvers were written, like these uncertainty, these numbers that represent uncertainty estimates? And it turns out that you can propagate these uncertainty estimates through the solver and get these beautiful error bars right out there for free without having to rewrite anything. And the person, Giordano, who wrote the measurements package and these APIs, was not imagining that the person who wrote differential equations might use them. But because the language provides abstractions that are good for composability, things come together. Here's another example, which is combining the Flux deep learning framework with differential equations. So you have a loss function, which instead of a regular function that of f of x is looking at the derivatives, And this is the Juno IDE and you can see the training in motion actually out here. As you know, the blue is the data and the red is trying to fit it, and it's solving an ODE inside the loop here. Now again, differential equations and flux were not designed to talk to each other, but with a little bit of effort, they now talk to each other, and we're able to do all sorts of fun, interesting things. So without further ado about what Julia can do, here's how you do it, and I'm going to hand over to Jeff.
Thanks. All right, hi everyone. So yeah, the question is, how do we implement all of that? How do we make all of that work? And I think when we write these programs, there are basically three things we want, which is easy, generic, and fast, where generic means you can reuse your code in different cases on different data types and so on, and easy and fast are pretty clear. And I think it's probably no accident that there are also three of us up here. We didn't just do this project with three people arbitrarily. I think you could make the case that for each of easy, generic, and fast corresponds to one of the three of us. I'm not going to speculate which is which, but but I think that might in fact be the case. And so we want all three of these. It's typically been very hard to get all three of them. As Viral said, the traditional approach is to actually bring multiple systems together and use multiple languages to try to get all of them, like wrapping C++ and Python, for instance. But we want to get all three at once. So we thought deeply about what you could do differently, if anything, at the programming language level to facilitate that. And so, inspired in part by the nested loops from Demel and Ongera of numerical linear algebra, those loops describe basically a kind of domain or a space of all the possible combinations of data types and structures and so on. Well, of course, you can't just write a program that just does all of that automatically. That's not really possible. It takes a lot of ingenuity to fully cover that space. But what we thought you could do is at least have a system that can describe the points in that space very well. So we wanted to have basically a standard formal way to describe where you were in a big domain like that. And then once you can describe something in a programming language, you're sort of 90% the way there. That gives you power over the thing that you can describe. And so the idea is we would describe it and then somehow generate code for it. So the core of the system is this sort of semantic domain or ability to describe what kind of structure and computation you have. So the sort of the recipe, if you will, for thinking about a program in the Julia way is to basically design some descriptive types for the domain you have. So you write down what are the basic objects and properties that they have, just design your types, and then you or actually other people can then just write methods for whatever cases you know about. So somebody can come along and say, oh, I know how to handle this case, here's a method for that. I know how to handle this case, here's a method for that. And those can be done entirely separately. And then throwing all of that together, the compiler basically composes it together and generates specialized code for the cases that arise. And the key to this is that these things need to be as decoupled as possible. So the person doing the first step, sort of designing the domain and the descriptions of the things we have, needs to be able to change that without affecting everybody later on. So you want someone to be able to increase the sophistication of the core definitions in the system without anyone else needing to change their code. So all of these phases have to be sort of very decoupled. And so that's what we tried to achieve. So as an example of what these elements of these domains that you can write down look like, here are some kinds of arrays or classes of kinds of arrays that you might talk about. So you might just have array, which means I know I have some sort of array, but I don't know anything else about it. Or I might know that I have an array of integers. Or I might also know that it's two-dimensional. Or I might know that it's two-dimensional but not know the element type. Or I might not know the element type, but I know it's some sort of real number. And so that sort of is that's one set of possibilities that's included in the base Julia library and our sort of default array type. But then some people want more detail and more refinement. So there's a package called static arrays where you can include the size in there. So with a static array, you have SArray, and you still have the dimensions and the element type, but you can also encode the dimensions of the matrix as well. And so then you will get specialized code specific to certain matrix sizes, which can be very important, of course. Some problems need that, some problems don't. And the key thing is that you can write code that just knows about arrays, and whichever one of these gets substituted in there, it still just works. So somebody else can decide that we need things to be specialized on array sizes, for instance, and then create one of those objects and pass it into your code, and everything continues to work. You don't have to adjust to that. And so the basic way we do that is by using kind of an unusual combination of dynamic typing, or duck typing, as Python calls it. But we have these very rich, sophisticated, nested structures of giving kind of type information. We're using sort of both of those at the same time, which is sometimes kind of unintuitive to people. But so as another example, and we use this everywhere in the system. We use it at all levels, everything from the tiniest scalar operation up to arrays or a whole plot or anything. So we can use this everywhere. So for even something as simple as adding an int and a float, we can represent that in our sort of domain or type notation. So 1 plus 2.0, its description in this kind of descriptive language is that this operation is just a tuple that has the plus object and an int and a float. And so the system thinks of everything you do in terms of this kind of language. And so in thinking about this as an object-oriented language, which it is in many ways, we've usually described this as multiple dispatch. Because instead of just selecting methods based on a single receiver, you can select it based on all of the arguments. And that is true, but it's actually even a little bit different than that, because we're not just looking at the arguments, we're actually looking at a whole structure. So there could be, each one of these elements in there could be a whole big structure describing something. So as an example of something useful you might define using this, so here is a so-called one-hot vector, which is a kind of fun term that occurs in the machine learning world, which is basically a vector that's 0 everywhere except for one place that has a 1. So of course that can be represented efficiently. You don't need to store all the zeros. All you need to store is the size of the vector and the index that has the 1. So you can define it like this. You can say a one-hot vector is a kind of vector where the element type will be bool. We picked bool just because you only have zeros and ones, so that's Boolean. And it contains integers for the index and the length. And then you just need a couple definitions that tells, this basically extends these functions that exist in the systems, telling it how to get the size of it, which is just a tuple of the length, how to get an element of it. So to get an element of it, if the index matches the one that has the 1, the answer is 1, otherwise it's 0. And then also and that's actually sufficient. So the first two definitions are enough to make this thing completely work with everything in the system. But I think then as a further optimization, whoever wrote this also specified a definition of multiplying a matrix by a one-hot vector. So that means abstract matrix means any sort of matrix with any representation times a one-hot vector can be done by just selecting the appropriate column, right? So it can be done in order n instead of n squared. And so this lets you have this very efficient representation of this kind of vector, and you can substitute it anywhere that expects a vector, and everything just works, and you get efficient code for it as well. So this is the exact same kind of technique that was used in Celeste for that fancy matrix structure that Viral showed, and we also use it in our standard linear algebra libraries to provide all the kind of structures you would expect, like diagonal, symmetric, bidiagonal, basically just slightly fancier versions of the same idea. And then these structures can actually get quite elaborate. So in one we did recently, I think this was from Flux, in the machine learning package, when you construct the neural net layers for this problem called VGG19, it actually, when you run the code to build up the structure, under the hood, it's actually constructing an object whose type is this. So in this case, this, we have there's sort of description of the structure of the layers of the neural net is sort of encoded in this descriptive language, and then this gets fed into the compiler, and it crunches through this and finds the methods it needs and ends up building the code for this. So the structures can get quite elaborate. So recently, actually, we worked with a PL research group at Northeastern to try to formalize some of what we were doing with these types that we have, and we had. And so these folks helped us out, and they helped us work out what was really going on with these structures that we're using in the language. And we wrote a paper about it. So it turns out that what you need to grapple with this and to make these things go actually looks something like this. So it's a bit hairy. I'm not going to talk through it, but this is what they came up with, and this was actually quite helpful. And we found various bugs, and we improved our system in fundamental ways as a result of this. So we're starting to figure out some theoretical underpinnings of what's going on in the system.
Skip this and go to step.
OK, maybe we'll come back to this later, but yeah.
Just briefly on this slide. One of the things that Julia excels at is exploring new data types. So the bfloat16 data type is a new data type that's natively supported on Google's TPUs. It's basically just a float 32 cut in half, so you lose all the lower digits. This is maybe 200 lines of Julia code to implement. Of course, it doesn't have hardware performance, but you can at least prototype things and see how the computations work, which is really powerful. And then it's fast when you run it on a TPU, because that actually has hardware support. Some other sort of programming in the future type of things that we have in the Julia ecosystem. People have done a lot of work and thinking about reproducibility, and sort of the state of the art these days seems to be make a Docker image and put all of the things that you use to run your code in that Docker image, and then someone can download that image and run it, and that's good because it allows reproducibility at least years later on totally different systems. But I don't know about other people, but for myself, I find installing and running Docker kind of a pain. I don't want to do it. It's annoying. So one of the things we've worked very hard towards is reproducibility by default, so as a built-in. So the way Julia code works these days since 1.0 is that in order to load code, you have these manifest files, and they're not written by hand, so don't worry, you don't have to generate this, but they're somewhat readable. And they basically identify the exact identity of the code that you were running and loading in your project. And it's a simple text file, and you can just commit it into your version control along with your source code. And then when you check that out later, years later on a totally different machine, wherever, you get the exact same versions of all of the Julia code that you're loading. And this is brilliantly simplifies reproducing what you were doing at some point in time. You don't have to worry about, oh, I upgraded this version of this package and this. Doesn't matter, different projects are independent, and you can tell someone to just clone something, instantiate it, and run it, and they're good to go. Also wonderful for reproducing bugs. We get bug reports with manifest files all the time now, and it's simplifies things so much, because you can just instantiate someone's manifest, and then you can reproduce their bug. So this is very much a programming in the future type of thing. Another fun bit of tech that we explored there were a lot of deprecations that we had to go through to get to the 1.0 stage that we did last summer. And so we have a bot that actually makes changes to people's code. It makes pull requests on GitHub to open source packages and says, hey, you should change this to this. And it's interesting because you could do this as a tool on your own, but people are lazy. They don't actually want to do that. So this is much better because now this friendly bot comes by and makes the changes for you, and all you have to do is look at it and say, oh, great, this is good. Hit PR, merge. Of course, you want to have some tests and CI to make sure that nothing broke. And occasionally the bot gets things wrong. And what happens is you can actually reply to the bot on the GitHub interface, and it files an issue on the bot's repo saying, you did something wrong, bad bot. That's actually the comment you write. You write bad bot, and then you describe what it did wrong. And you can see it has this cute little message that says it's been updated, and some philosophical conundrum about being the same bot or not. So it's, Julia is now already a global community. I mean, even when the three of us started out, we were in at least 2 continents because Viral was in India. But now, Julia is all over the world, and you can see this heat map is where, where a lot of contributions are coming from, and it is truly everywhere. We've also, seen a meteoric rise in stars on GitHub, which is, a poor proxy for who's actually using it, but I mean, clearly it's going up and to the right very rapidly. And we all know exponential growth is not fundamentally sustainable forever, but we've got a while to go, I think. And there's a lot of books these days that have not been written by any of us, but excellent textbooks on Julia as a general purpose language, on Julia as a high performance programming environment, on data science in Julia, computer vision, operations research, and one I'd like to, applied linear algebra. I can't skip that one. That's actually near and dear to all of our hearts. I'm going to focus a little bit on one that is not, it's in pre-release. It is by Michael Kokendorfer and Tim Wheeler, and this is just a beautiful, beautiful book. Coming out next month, so it's in pre-order right now. And one of the cool things about it is, it's gorgeous, right? So it's really nicely typeset, LaTeX, and nice inline Julia code, and you can see some of the good use of Unicode characters in Julia. And even though Julia has this type system, a lot of simple code just doesn't need it. You don't ever have to mention types. They just get, they get used internally for you to produce efficient code, but you don't have to worry about them yourself. This entire book is generated by a Julia program, which not only includes the text and then generates the figures, but also runs the code that generates those figures and generates all of the output that's included in all of the examples. So it can't be wrong. It's basically, this is the future way. This is how textbooks are going to be made going forward into the future. And here's a chunk of Julia code, because you can't have a talk without showing any of the code in a programming language. And you can see it's very straightforward. This does a direct optimization algorithm. And here's one of the beautiful graphs that is generated in this. And so anyway, it's a lovely book. I'm excited to get my copy. Julia is being taught all over the place now. You can see this, we could barely fit in all of the, this is even only some of the universities. I sort of selected some of the universities with nicer logos. And a little bit of variety, but this is, this shows you that this is really all over the place, and people are having great success teaching, I think, especially in numerical areas, but not necessarily limited to that. And just as a final thought, Guy Steele is, one of the most famous programming language designers and architects of our era. And one of the things he said was a main goal in designing a language should be to plan for growth. And the language should start small, but then it must grow as the set of users grow. And that's, this idea of composability and allowing people to implement really fundamental, things that would normally need to be built into the language in other systems, allowing them to implement those as external packages, that's really very much in line with that philosophy, and that's what we're trying to accomplish. So thank you all very much.
Well, thank you very much. It ran just a touch over time, but I took the prerogatives of the chair to let time go by. But on the other hand, it also means that I'm not going to take any questions, but they will be around to answer any questions you may have. So once again, let us thank them.
Thank you.
Thanks. Thanks.